Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over another example of molecular orbital theory. This time we're going to be looking at the molecular orbital diagram for group 2, or I'm sorry, a period 2 molecule, or diatomic, or diatomic homonuclear molecule. So that means that we're looking at a molecule that's made up of the same two atoms. So in this case, we're looking at nitrogen that has N2 as its formula. Now, with regard to the orbital diagram, so here's the orbital diagram for the valence electrons, or the valence shells or sublevels for your molecule. We're ignoring the core electrons, so you'll notice that we start at 2s. We could add 1s down here. The only difference between the 2s and the 1s is that it's made up of 1s orbitals. So it looks exactly like this, except instead of having 2s and 2s, you have 1s. So this is the valence electron portion of it. So you could do this without the core electrons. And so the problem here we're going to look at is we're given three different molecules of nitrogen. You have the neutral charge nitrogen, you have the nitrogen that is a negative charge on it, and you have nitrogen with a positive charge. And so all you need to do is know the order of the molecular orbitals. And this is again how you set it up. So if you got your molecular orbitals in the middle, those are going to be made up of the atomic orbitals on the side. So you have your atom. So you got nitrogen atom on this side, you've got a nitrogen atom on this side. Each nitrogen atom has 5 valence electrons because it's in group 5. So you would put 5 valence electrons in here and here. And then the total number of valence electrons that you have are going to be added to the molecular orbitals, and using the rules and the principles we used before. Aufbau principle, where you're going to start low energy and work your way up. You've got the Pauli exclusion principle, where each molecular orbital holds a maximum of 2 electrons, and those electrons must be opposite spin up and spin down. And finally, Hund's rule, where if you have molecular orbitals of the same energy, you're going to put an electron in each of those, same spin up first, and then you would add spin down to them afterwards. And so then that's how you do your molecular orbital diagram, which is exactly the way you would do it for your atomic orbital diagram when you learned about atomic orbitals and electron configuration and things like that. So the rules apply here as well. All right, so let's get into this. So with regard to these three, we can fill in the orbital diagram and see which one is going to have the stronger bonds, which one's going to have the higher bond order, which one's going to have the shorter bonds, things like that. So you can compare all three of these by filling in the electrons. So let's start with the neutral atom, N2. And so we know that each nitrogen has 5 valence electrons. So 1, 2, 3 there. And this one has 5 valence electrons. So paired in the 2s. And then you've got 5 there. Okay, so now that's for our neutral atom. And so when you add these together, we got 10 total electrons, so we're going to fill them in. So we're going to start here, 1, 2, 3, 4, and then Hund's rule, 5, 6, 7, 8, and then 9, 10. So from this we can determine different properties, right? So is this going to be paramagnetic or diamagnetic? Well, we don't have any unpaired electrons, so we would expect this to be diamagnetic, no magnetic properties. We can figure out the bond order. So the bond order for N2, right? So the bond order is going to be number of electrons in bonding orbitals. We have 2 here, and we have, let's see, we have 2 here, we have 4 here, so that's 6, and we have 2 here, so 8. So 8 minus electrons in the antibonding. So we have 2 here, and that's it. So minus 2 divided by 2, and that gives us 3. So 6 divided by 2 is 3. So we would expect our nitrogen to have 3 bonds, and that's what we do get. Okay, so what about N2 minus? So if we have a minus here, then that means that one of our atoms gained an electron, so we can put it there. And so we'll need to pair up one of these. Okay, so now we have 6 on this side and 5 on this side, which means that we have a total of 11. So now we need to add another electron here. So we're going to have to add an electron to an antibonding orbital. So that's going to be spin up, putting it into the pi star 2p molecular orbital. And so now we can do the calculation. So we could do N2 minus bond order. And that's going to be equal to, again, we have the same number of bonding. That's going to be 8. And then we have 2 here in the antibonding and 1 here. So that's going to be 3. So minus 3 divided by 2. And now that's going to be 2.5. So that's going to be equal to 2.5. So now the bonding order is, instead of 3, is now 2.5. Right? So now we have a fractional bond here. Okay? And now we can say things about this molecule here, certain properties. We could talk about the fact that it has an unpaired electron. So we would expect this molecule or ion to have magnetic properties because it is now paramagnetic. Its bond order is smaller than that. So we would expect the bond here to be weaker, to be longer, and so on. All right, now what about N2 plus? In that case, instead of gaining an electron, we lost an electron. So instead of pairing up an electron, we lost one. So here we have a plus sign, and here we have a plus. And so in that case, we won't have this electron here, but we're actually going to lose an electron there. So we have 1 less electron. So again, we could calculate the bond order of N2 plus. So for N2 plus, the bond order is going to be equal. Again, now this time our number of the bonding electrons has decreased. So we have 2 here, 1, 2, 3, 4, 5, 6, and 7. So we have 7 minus 2 of the antibonding, 2, and we get 5 again divided by 2, and then again that's going to give us N. So we got, that's going to be equal to 2.5. So 2.5 again. So again, we're going to have a weaker bond. Lower bond order means weaker bond, longer bond, compared to nitrogen, N2, neutral. And again, we have an unpaired electron, so that means that we're going to have magnetic properties because it's paramagnetic. So this is the way, again, that you would use molecular orbital theory to figure out the properties of your atoms, to compare different different molecules, whether you've got neutral, negative, or positive charge. It all comes down to, again, the orbital diagram and the number of valence electrons you have. As long as you know the order of the molecular orbitals and the number of electrons that you have in both atoms or in your molecule as a whole, you just add those electrons and then look at what it tells you. Okay? I hope this was helpful and clear. If you like this video, like it, hit the like button, hit the bell notification so you can get notified of any other videos. Share this video. Subscribe to the channel. Make a comment in the comment section. Let me know what you think and if you have any questions for me. Thanks for joining me, and I'll see you later.